Good morning, everyone. In today's lecture, we're going to solve problems about linear momentum and collision. Let's start with the first one. So we have two blocks that are free to slide along the frictionless wooden track ABC as shown in the figure below here. The block of mass M1, which has a value of 5 kilograms, is released from A. So at this point, the block M1 is released, which means it has a velocity equals to 0. Protruding from its front end is the north pole of a strong magnet, repelling the north pole of an identical magnet embedded in the back end of the block of mass M2 equals 10 kilograms, which is initially at rest. So here is a summary. At the end of each block from both sides, so from this side for M1 and from this side for M2, you have the north pole of a magnet, and both magnets are identical, such that when M1 it goes and approaches B, it will not touch, but it would just make a collision between M1 and M2, and it's going to be a repelling force. So, and M1 is released from rest, while B, the block B, is at rest, is not moving. Now, the two blocks never touch, and you have to calculate the maximum height to which M1 rises after the elastic collision. So let's actually just draw these 3 steps of the motion. So the first steps for M1, let's just talk about M1. The first step of the motion for M1 is that M1, it goes from point A to point B, right? And when it arrives, so let's actually say, let's just define everything. So at point A, it has V1 initial, let's call this V1 initial equals 0, because it was released at this point. And at point B, let's say that it has some velocity V1, which means that when the block M1, it arrives at this point in here, and just right before the collision, right before the elastic collision with M2, it has a given velocity V1. Now, this is the first step. The second step is the elastic collision between M1 and M2. So up in this collision, what happens is that block M1 will rebound with a given velocity. Let's call it V1 final. So V1 final is the velocity of the block M1 right after the collision. So after the collision, what happens is that the block M1 will just rebound with this V1 final. Okay, and then it will go up the track up to a given height. So we don't know what is this maximum height. We are looking for it. So let's assume that it comes to this point. So at this point, we're going to call it H, and this is the height, the maximum height that it could reach. So the third step of this motion then would be that M1, it goes from the point B to the point H, and it has, at point H, it has V1 final as so it has V1 final as initial velocity because it just happens right after the collision. And at point H, we should have VH equal to 0. Why? Because simply we're looking for the maximum height, and the maximum height corresponds to the time when the block M1 stops moving. So basically VH is equal to 0. So what we need, so from this first step, we need to determine V1. From this step, we need to determine V1 final. And from this step, we can actually determine the relation between V1 final and H max, so that we can guess what is the maximum height reached by the block M1. That's it. So we can do them in different orders. Let's start with the first and then go down. What happens? So from the first step, number 1, what we have is the following. So between point A and point B, the block M1 is moving on a frictionless track, and there's no non-conservative forces acting on the block M1, given that also there is no friction, which means that the mechanical energy of the block M1 is conserved. So we can write down the mechanical energy of the block M1 at point A is equal to the mechanical energy of the block at point B. And so we can write down the mechanical energy at point A. It corresponds to the initial kinetic energy and the initial potential energy. So for the kinetic energy, we have 0. Let me just write it down. So we have the kinetic energy at point A plus the potential energy at point B, at point A, pardon, is equal to the mechanical energy at point B, which corresponds to the kinetic energy and the potential energy. Now, of course, for the potential energy, if you just have to look what you have. So in our case, we only have gravitational potential energy because we don't have any spring in there. So at the point A, the kinetic energy is 0 because the block was released. And at block B, while the gravitational potential energy is different than 0. And at point B, the kinetic energy is definitely different than 0. And we are looking for the velocity at this point, for the speed, while the potential energy, actually, it can be 0 if we take the proper choice of a reference. So let's take this reference, this level, to be our reference for gravitational potential energy, which means that YB is equal to 0, because this is the level Y equals 0, right? And if YB is equal to 0, that means UB is equal to 0. So the potential gravitational potential energy at point B for the mass M1 is equal to 0. And so from here we end up with the following. So the M1 times G times H, this is the gravitational potential energy of M1 at point A, is equal to half M1 times V1 squared. And from here you can deduce that V1 is equal to square root of 2G and H. That's it. Okay, so that was step number 1 from the first part of the motion. Now, for the second part of the motion, we can simply use, actually in this case, the expression for, so we consider the case of an elastic collision between two masses, M1 and M2, and we have derived the proper equation for the velocity of both M1 and M2 after the collision. And so you just need to apply this expression in here. So you end up with V1 final is equal to M1 minus M2 divided by M1 plus M2 times V1. And don't forget that there is also here some term which is, in this equation, there is a term which is multiplied by V2, right? So V1 and V2, they are the initial velocity of the particles M1 and M2. But since M2 is at rest, then V2 is equal to 0, and we are only left with this part of the equation, which is M1 minus M2 times V1 divided by M1 plus M2. And here just need to make a numerical application. You end up with minus 1 over 3 V1. And V1 we have already calculated is equal to square root of 2GH. So that is done, and this is done. We have V1, so we have V1 final. And V1 final, of course, depends on V1, which we already have. The last step is then now to calculate what is H max. So again, here, we are going to apply the same thing that we have applied before, which is the conservation of mechanical energy. For the particle, or for the block M1, when actually right after the collision, it rebounds and it goes up the track. So again, it's going up a track which is frictionless, so there is no friction working on the system, and there are in general no non-conservative forces acting on M1, which means that we have conservation of the mechanical energy of the mass M1. And so we can write down then the mechanical energy at point B is equal to the mechanical energy at point H. So at point B, that means we have the kinetic energy at point B plus the gravitational potential energy at point B is equal to the kinetic energy of point H plus the gravitational potential energy at point H. And again, here we do the same reasoning. So at point B, we have taken the level where the point B is to be our reference for gravitational potential energy. So this is equal to 0. And we know that the particle, we are looking for the maximum height reached by M1, which means the point where M1 stops moving, which means KH is equal to 0. So there is no kinetic energy for H because for the M at point H, because M has zero velocity. So that's it. We end up with K, the B is equal to UH. So the kinetic energy at point B, where we have here V1 final, it's the velocity of the block M1 right after the collision, equals to M1 times G times H max. And so we end up with H max equals V1 F squared divided by 2G, because M1 cancels on both sides of the equation. So we know what is V1 final. All what we need to do is to just make a numerical application. And so by making numerical application, we end up with the value 0.555 meters. So that's it for this problem. Let's move on to the next problem. As shown in the figure below, a bullet of mass m and speed v passes completely through a pendulum bob of mass capital M. The bullet emerges with a speed of v divided by 2. So it comes with a speed v and then emerges with half of its initial speed. The pendulum bob is suspended by a rod of length L and negligible mass. What is the minimum value of v such that the pendulum bob will barely swing through a complete vertical circle? So our question then is to calculate the minimum value of the speed of the bullet such that this bob will make a complete revolution. So we all know by now what would be the condition for a given object that is connected to a rod to make a complete revolution. But let's actually repeat this again. So if you want this bob to make a complete, just forget about the bullet at the moment. If you want this bob to make a complete revolution, we should just have a look at point B. So it's called B for bottom. And it should actually pass by this point, which is the top point. If the bob B is able to pass this top point, I'm going to go with T for top, then there will be no problem and the bob will make a complete revolution. But if it fails to arrive to this point, then it will drop before and then it will not be able to complete one revolution. So let's have a look at this point in particular. So at this point P, what forces do we have when the bob is in here? So when the bob is over here and it's still connected by this rod, okay, so it's a stiff rod actually. So what forces do we have in this case? We do have the following. So we have, first of all, the weight. Let's just make it in here. So this is M times G, and it's mg, where M is the mass of the bob, right? And then we have the tension in the cord, T, and we do have as well don't forget that the centripetal acceleration is all the time here because we are dealing with a circular motion. So the centripetal acceleration points all the time towards the center of the circle. You don't forget this. So if we apply Newton's second law on the mass M at the point on M at the point T, what do we end up with is the following. So we have T plus mg is equal to M times A. So here I just didn't do any I didn't put vector because I immediately made a projection along this centripetal direction. And so we end up with T equals mg minus AC, or AC minus G. AC minus G, right? So now, what is the minimum value of the tension? So the tension should be all the time greater than 0, right? And so this means that AC minus G should be all the time greater than 0 because this is the difference to which T is proportional. And that means that AC should be all the time greater than G. Now, what is the centripetal acceleration at the point T? It's given by the velocity at the point T, so Vt squared divided by the radius of the circle. And so we end up with the following relation. So Vt squared over R should be greater than G, right? And from this equation, we're going to extract the minimum value of the speed of the bullet. Now, this is the way we're going to do it. So the velocity or the speed of the bob at point T, okay, it depends, or we can get it from the point B because we know what is the speed of the bob at point B. And how can we know the speed of the bob at point B? It's because we have some inelastic collision with between the bullet and the bob, right? So what did they say in the given? So they say that the bullet passes completely through a pendulum bob, and it emerges with a speed of v over 2, where v is its initial speed. That means that we have an inelastic collision between the bullet and the bob, because it passes completely through it. So there is kind of a deformation of the bob after the collision. And so what we are going to do is that we're going to take the equations for the inelastic collision between the bob and the bullet. We're going to determine what is VB. And then from VB, we're going to deduce or determine what is VT. And then we replace VT by its expression in this equation. So let's actually do it. It's very easy. Let's start first with the first event, which is the inelastic collision between the bullet and the bob. So between the bullet and the bob, we have inelastic collision, right? So what do we know about inelastic collision? We know that the momentum is all the time conserved for the system M1 and for the system bullet and the bob. And so we can write down that the P initial, so P, the linear momentum before the collision, is equal to the linear momentum after the collision, right? So we end up with the mass M multiplied by the speed of the bullet, or let's just detail a little bit and put it in the details. So we end up with P. Let's call the bullet 1, right? And so let's call the bullet 1 and the bob 2, particles 1 and 2. So we end up with P1 initial plus P2 initial is equal to P1 final plus P2 final plus P2 final, right? And so here P1 initial is given by the mass multiplied by the velocity. So here we're taking, this is the x direction, right? This is the direction of the motion. It's m times v plus the P2 initial is simply 0 because the bob was at rest. That is equal to, so P1 final, what is the momentum, the linear momentum of the bullet after the collision? Actually, the bullet, it emerges from the bob with a speed v divided by 2 in the same direction as its original motion. So it's m times v over 2 plus P2 final is the linear momentum of the bob right after the collision, which is the mass times its speed. So we are going to call it VB, right? So that's it. Here we can actually deduce how much is VB as a function of V. So we end up with m over 2 times V is equal to m times VB. And from here we can deduce that simply VB is equal to 2m over m times V, where V is the speed of the bullet. Now, so we get what is VB. Now, all what we need to do is to see how much is VT if we know that VB is equal to 2m over m times the speed of the bullet. So what should we apply here? So actually, between point B and T, the bob is under conservative forces only. And if we consider the system bob and Earth, we're going to see, or we can check, that the mechanical energy of the system is conserved. And therefore, so between point B and T, we have conservation of mechanical energy. That means that the mechanical energy of the bob at point B is equal to the mechanical energy of the bob at point T. Okay, that sounds great. Now let's just put them a little bit in detail. So we end up with the kinetic energy at point B, and the potential gravitational energy at point B is equal to the kinetic energy at point T plus the gravitational potential energy at point T. Now, if we take this to be our reference for, so this level, the level where the bob has been in the initial position, is our reference for the gravitational potential energy. Okay, then we end up with UB is equal to 0 because it's at the level, at the reference level, okay? And in this case, of course, UT is different than 0. So the gravitational energy of the bob at the point T is different than 0. So how much is it? We end up with, so just going to continue here, we end up with half mVB squared is equal to half mVT squared plus, so the gravitational potential energy is given by the mass times g times the height from where the point is with respect to the reference level. And if you can see, this is nothing else than 2 times L, where L is the length of the stiff root. So we end up with 2 times L, right? So just now we need to cancel out all the mass terms. So we end up with VB squared equals VT squared plus 4G times L. So don't forget that we have canceled. So we just have multiplied everything by 2. So this cancel out, get this cancel out, and this factor becomes 2. And so we can write down that VT squared is nothing else than VB squared minus 4GL. So we know by now what is the value of VT, and all what we need to do is just to replace it by its value in here. So we end up with the following. So we end up with VT squared over R would be equal to VB squared divided by, so VT squared is equal to VB squared minus 4GL, right? So R is nothing else than the L. So R, don't forget, it's equal to L, right? So VT squared over R is nothing else than VT squared over L, okay? So it is VB squared divided by L minus 4GL divided by L, so L cancels out. And then here we just replace VB by its value. So VB is, as we have seen here, 2m over m times V. So we end up with squared, we end up with 4m squared divided by m squared, right? Multiplied by, so this is 4. Let me check just one thing before. Okay. So we end up with, actually here there's just one thing which is wrong, which is it's m over 2m times v and not 2m over m. So it was a typo. It's m over 2m times v. So let me write this down in here. So we end up with vt squared over r. R is nothing else than L, so Vt squared over L is given by, Vt squared is given by VB squared minus 4GL divided by L. So we end up with VB squared over L minus 4G. And now we have to replace VB by its value. So again, VB is given by m over 2m times V. So VB squared would be equal to m squared divided by 2m becomes 4m squared, right? And then we multiplied by V squared multiplied by again, so this is not, sorry, it's a small m over capital M. So small m divided by 4 capital M squared multiplied by V squared, and then we have L in the denominator, so we end up with L in here minus 4 and times G. Now, we know that Vt squared over L should be greater than G, which means that, let me just write it down in here. So we end up with Vt squared over L is greater than G. That means that we should have m squared divided by 4m squared L, V squared minus 4G should be greater than G, which means that what I'm doing in here is just what is written over there. It's, we end up with V squared multiplied by m squared over 4 m squared L should be greater than 5G. And so we end up with V should be greater than, we just have to take the square root, right? So, or in other words, we end up with V squared should be greater than 4m squared L times 5G divided by small m squared. And if you just make a square root here, you end up with V equals, so V should be greater than instead. So we end up here with 2 times 2. So we end up with 2, or let me just write it down, 2m over small m multiplied by square root of 5 times G times L. And this is what we get over here there. So this is the solution. And of course, the minimum value would correspond to this value, which is on the left-hand side of the equation or right-hand side of the equation. We move on with the third problem. So in this case, we have three cars of masses 4, 10, and 3 kilogram move on a frictionless horizontal track with speeds of 5 meters per second, 3 meters per second, and 4 meters per second, as shown in this figure. So Velcro couplers make the cards stick together after colliding. So actually there is some kind of couplers which is fixed on each of the cards such that whenever they collide, they stay together, they stick together. The point is that we have to find the final velocity of the train of three cards after the collision. Right? That's in the first part. Now the second part, they say, what if the cards collide and stick together at the same time? So if actually the cards collide together and stick together at the same time and not one by one, then in this case, what would be the difference between your answer, okay, and the answer when actually they collide in different order? So let's say that, for example, you have let's call this M1, M2, and M3, right? So just to make it more clear. If the three cards, so we have two choices basically, or two options. The first option is that they collide at the same time together. They collide together at the same time, which means M1, M2, and M3, they collide at the same time together. So in this case, at a given time t, all of them, they will collide. The second option would be different. So the second option, there are different possibilities. For example, it could be that M1 collide with M2, okay, at a given time, and then the train of M1 and M2 collide with M3, right? It could be that, for example, you have M2 collides, or yeah, you have M2 collides with M3, and then the train M2 and M3 collides with M1. So in this case, we talk about order, because they do not collide all at the same time, but they collide in order. So the question in second part, what would be the difference between these two? If they collide together at the same time, or if they collide in order? Is there any difference in the answer? That's the question. Now let's go to the part A and then solve it, and then go back to the part B. And the part A, they say that the three cards, they are moving on a frictionless horizontal track, which is very interesting, or at least we should note that it's frictionless horizontal track, and they collide and stick together. So they make kind of train of the three cards. So the question is, what is the final velocity of the train? That's it. First of all, before solving this problem or question, we need to categorize the collision. Is it elastic or is it inelastic? What happens in this case is that the three cards, they stick together. So they make kind of one body, and this one body will move by itself, which means that we have an inelastic collision because the state of the system has changed between the initial and the final state, so before and after the collision. And so this is why we just need to apply the conservation of linear momentum between the time before the collision and the time after the collision. And don't forget that here we're just talking about the time right before the collision and right after the collision. So right before the collision, these are the different components of before. So P1 plus P2 plus P3, which are given by M1 V1, M2 V2, and M3 V3. And the linear momentum right after the collision is equal to the mass of the system multiplied by the velocity of the system, where the system is composed of the three cards. So this is why we have M1 plus M2 plus M3 multiplied by the speed V. Now, all you need to do is just to make a numerical application in here. So we end up with V as a vector is equal to M1 V1 plus M2 V2 plus M3 V3 divided by the sum of all masses. Now, you have just to take into account that we have a direction in here. So let's take this to be our X direction. Okay, you can see that both M1 and M2, they move in the same direction, while M3 moves in opposite direction with respect to M1 and M2. So you just have to take this into account while making the projection in your equation. And so you end up with 20 plus 30 minus 12 divided by 10 plus 4 plus 3, which is 17. And so you end up with the value 2.23 meters per second along the x-axis. So we just here put the projections with the unit vector, because here we are dealing with a vector. So this is the answer of the first part. Now let's move to the second part and then check whether the answer change if you just take an ordered collision, or if you just take the collision to happen at the same time between all the elements of your system. So to make sure if the answer changes or not, what we're going to do is that we're going to take these two different orders, and then we're going to check the answer in each case. Okay, so let's start doing it. Okay, if we consider the case M2 and M3 collide together, and then M1 collide with the system M2 and M3. So what we have in this case is the following. M2 and M3, because we have some couplers, right? Then the both will stick together. So we'll end up with M2 and M3 as one system, right? So this system will have a given velocity v23, just to say that this is the system of the speed of the system 2-3. And then we have the block M1, which is still moving with its velocity v1, right? So this would be our system. Now what we need to do is just to calculate v23, and then after this we will make the collision between M1 and the system M2 and M3. So these are just the couplers, right? M3, and then we are going to see what is the speed of this system, of the total system M1, M2, and M3. But in this case, the collision happened in order. So between M2 and M3 at the initial time, and then later on with M1. Okay, so again, here we will just apply the conservation of linear momentum for this collision, for the first collision. So we end up with P initial is equal to P final. So P2 plus P3 is just equal to the P after, right after the collision. I would just call it P23, right? So we end up with M2V2 plus M3V3 is equal to M1 is equal to M2 plus M3 times V2, 3. Okay, so we know everything. All we need to do is just to now deduce what is the value of M23 or of V23. So we end up with M2 is equal to 10 times V2 is equal to 3, and this is along the X direction, plus M3 is equal to 3. V3 is equal to minus 4 projected along the X-axis, divided by M2 plus M3 would be equal to 10 plus 3, so it's 13. If you just make the numerical application, you end up with actually 1.38 I. 1.38 meters per second along the X direction. And so now we know what is V23, and we are going to consider the collision between M1 and the system M23. So if we again apply the conservation of linear momentum for this system between initial and the final stage, which corresponds to the time right before the collision and right after the collision, we end up with, so M1V1 plus M, so the mass of the system 2-3 multiplied by the velocity of the system 2-3 is equal to M1 plus M2 plus M3, so mass of the new system multiplied by its velocity V, where V is the velocity of the total system. And so you end up with V equals to M1 V1, so M1 is nothing else than it's 4, I think, yeah, it's 4, multiplied by V1 is equal to 5, plus M23 is 13, we have just seen this before, multiplied by V23, we just drive it in here, it's 1.38. So all of this is along the X direction, divided by 13 plus 4, which is 17. And so if you just make the numerical application, you end up with the same value as we have seen in part A, so 2.23 meters per second along the X direction. So from this first test, we check that if you take all the cards to collide together, or if you take the cards to collide in different order, you end up with the same result. So actually the answer does not depend on the order of the collision and does not require the cards to slide at the same time. And here you just can find the other exercise where you can also know. Here you have this you have one exercise, but actually you can do the other one, which is the case where actually you just can do it as a test. You just take M1 and make the collision between M1 and M2 at the beginning. So you'd have this M1 and M2, and the system M1 and M2 would be moving with a velocity V1, 2, and then take later on M3 to collide with the system while M3 is moving with its speed or velocity V3. Just as we did in here, you will find that you just end up with the same answer because the order of the collision makes absolutely no difference in the final result. So that's it for this problem. Final exercise. A 5-gram bullet moving with an initial speed of 400 meters per second is fired into and passes through a 1 kilogram block as seen in this figure below. The block is initially at rest on a frictionless horizontal surface, and it's connected to a spring with force constant 900 Newton per meter. Now, if the block moves 5 centimeters to the right after impact, you have to find the speed at which the bullet emerges from the block, and you have to find the mechanical energy converted into internal energy in the collision. So in this case, what happens is that you have this bullet, and this bullet, it passes completely through the block of mass 1 kilogram at a initial speed of 400 meters per second. Now, after the collision, what happens is that the block will move 5 centimeters to the right. And we have to find the speed at which the bullet emerges from the block. That's number one. And the mechanical energy, how much of its mechanical energy is converted into internal energy in the collision. So let's start with the part A. So in part A, we need to determine the speed at which the bullet emerges from the block. We know that what happens between the bullet and the block is a collision which is inelastic because the bullet passes through the block. And so we can apply the conservation of linear momentum for the system, bullet, and block between the initial and the final state. Initial means right before the collision, and final means right after the collision. So we end up with, let's say in other words, P1 initial plus P2 initial, where 1 it refers to the bullet and 2 refers to the block, is equal to P1 final plus P2 final. Now, P1 initial is different than 0 definitely because it's equal to the mass of the bullet multiplied by its speed V. P2 initial is simply equal to 0. P2 initial in here, sorry, so this is a typo. It's P2 initial. P2 initial is simply 0 because the block is at rest. It is equal to P1 final. So P1 final is nothing else than the mass multiplied by the speed of the bullet that we are looking for. So let's call it V1 final. Plus P2 final is M2. Let's call it capital M, or just call it M2 since it's not given multiplied by V2F. Okay, so we are looking for this V1F. V is known, M1 and M2 are known, but V2F is not known. So we need to determine first V2F and then put it back into this equation. Now, what do we know about the block 2, about the block, which we call it M2? We know that right after the collision, this block has moved on the horizontal surface and it made a compression of the spring by 5 centimeters to the right. So since the block is moving on a frictionless surface and there's no conservative forces acting on the block, then we can say that the block and the earth represent a conservative it's just an isolated system, and the mechanical energy of the system is conserved. So we can say that the mechanical energy of the block right before the collision should, like, let's say just at this point here, I'm gonna call it I, is equal to the mechanical energy at the position where it compresses the spring by 5 centimeters. So EMI is equal to EMF, where EM represents the mechanical energy. So at the initial position right after the collision, the block has a given velocity, which is V2 final. So we end up with half M2 V2F squared, so this is the potential energy, the kinetic energy, pardon. For the potential energy and the initial position right after the collision, there is no potential energy, neither gravitational nor elastic, because the spring has not yet been compressed. And we take this to be our reference for gravitational potential energy. So that means that we take our reference, or we take the position of the block to be our reference, which means the gravitational potential energy is 0. This is equal to, in the final position, actually we have, of course, so the gravitational potential energy is 0. The elastic potential energy is different than 0. It's equal to half times k times, it's called just x squared. And for the kinetic energy, we have it to be equal to 0, because in this position, the block did not move further. And so we end up with V2 final equals, so V2F squared, let's just keep it, is equal to k times x squared divided by m2. So if we know what is the expression of V2 final, then we can put it back into this equation, and then we get what is the expression of V1 final. So we end up with, finally, just combining the two equations, we end up with, so V1 final is equal to V simply, okay, minus M2 over M1 times V2 final, and V2 final is equal to the square root of kx squared divided by M2. That's it. So all we need to do now is just to make a numerical application for this one. So you end up with, as we have written, so V1 final is equal to V, I called it, minus M2 over R1 times square root of kx squared over M2, and you end up with 100 meters per second, which is the value of the speed of the bullet right after the collision, so after it emerges from the block. So we continue with the last question. Here it's written, we have to determine the mechanical energy that is converted into internal energy in the collision. So to do this, the best way is to calculate how much the mechanical energy has changed. It has been modified by how much. And to do this, all what we need to do is simply the difference in the mechanical energy between the initial state and the final state. So the initial state would correspond to the case where the bullet, it comes into the block, and it comes into the block, right? And the final state would be when the bullet emerges from the block and the block has moved by 5 centimeters. So this is how we do it. So delta EM is equal to delta K plus delta U, where K is the kinetic energy and U is the potential energy, which includes both gravitational and elastic. So delta K is K final minus K initial, and delta U is U final minus U initial. So in what concerns the bullet, there is a difference in its kinetic energy, because it comes with 400 meters per second for its speed, and it goes out, or it emerges from the block with 100 meters per second. So this would be the difference in the kinetic energy for the bullet. For the block, actually between the initial and the final state, there is no variation. The block before the collision, right before the collision, it has a 0 speed, and when it compresses the spring by 5 centimeters, it also has a 0 speed. So this is why we don't have any factor for the kinetic energy for the block. But we have the spring. The spring changes the position from equilibrium to 5 centimeters. It was compressed by 5 centimeters, and this is why we have some variation in the potential, elastic potential energy for the spring. So if you just apply the numerical application, just make numerical application, and you put all the numbers, and you end up with delta EM is equal to minus 374 joules, which means that there was a loss in this collision of 374 joules, and this is the amount of internal energy to which the mechanical energy was converted. So that's it for this problem.